Hi everyone, I'm Alexander. I'm a third year TP in Trinity, and today I'm going to be teaching you about index notation, the Levi-Civita symbol, and Einstein Summation Convention. Okay, so let's first consider a vector, a three-dimensional vector, v, with components or entries v1, v2, v3. Now with index notation, we can write that as v sub I, where I can take the values 1, 2, or 3. Let's look at another example that should be familiar, the displacement vector in Cartesian coordinates. So here, the entries are not labeled with a number, but rather x, y, and z. That's just the convention, right? So here, x sub 1 would be equal to x sub 2 would be equal to y, and x sub 3 would be equal to z. Okay. Now, why is this useful? Let's look at how to express the dot product using index notation. So the definition of the dot product of two vectors is, let's say we take v dot u, that's equal to the sum of the product of their components. So that'll be v1, u1, plus v2, u2, plus v3, u3. Now, you might already be able to see how we're going to simplify this using index notation. We can write this as the sum, as I goes from 1 to 3, of vi, ui. Okay. Now, this brings us to the definition of the Einstein Summation Convention. In this case, the summation symbol is not so cumbersome. We could probably just leave it and everyone would understand it. However, when we're dealing with terms which have loads and loads of different factors in it, all with their own indices, and we have to keep track of 4 or 5 indices being summed over with different limits, it gets a little bit overwhelming. So the Einstein Summation Convention says that whenever an index is repeated, we sum over that index. That's known as the Einstein Summation Convention. Okay. Well, I showed you how to write the dot product in this convention. It would just be v sub I, u sub I, where since the index I is repeated, that tells us that we have to sum over it. But what about the cross product? Well, first I have to introduce a new symbol called the Levi-Civita symbol, and it's defined in this way. Epsilon sub ijk is equal to plus 1 if the indices I, j, k are an even permutation of 1, 2, and 3. It's equal to minus 1 if they are an odd permutation of 1, 2, and 3. And it's equal to 0 if any of I and j, k are repeated. Now, by repeated I mean if any of I, j, k are equal. So for example, if I is equal to j, if j is equal to k, or if I is equal to k, then this symbol is equal to 0. Okay, and what do I mean by a permutation? Well, let's take 1, 2, 3. A permutation is just switching 2 of the numbers around. So for example, 1, 3, 2 is just one permutation of 1, 2, 3, right? Because I just switched the 2 and 3. And then if I did it again to get 3, 1, 2, well, that would be another one, right? So in general, if the arrangement of I, j, k here is such that it's an even permutation of 1, 2, 3, so an even number of arrows away, then that symbol is equal to plus 1. And if it's an odd number of permutations away, then it's equal to minus 1. Okay. Well, it might be helpful if we just wrote out a few of these symbols, right? So what is epsilon 1, 2, 3? Well, 1, 2, 3 is 0 permutations away from 1, 2, 3. That's an even number. So it's just equal to plus 1. What about epsilon 3, 2, 1? So to work this one out, you should probably start by rearranging it back to 1, 2, 3, and then counting how many steps that was. So let's see. So 3, 2, 1, we probably want to bring the 1 to the front. So that'd be, the first step we would do is bring it to the middle, and then we bring it to the front, and then we bring the 3 to the back. Okay, and how many steps was that? That was 1, 2, and 3. So it's three permutations away. That's an odd number. So so it's equal to minus 1. Okay, and finally, just to make it clear, let's say we had epsilon 1, 1, 2. Well, here the index 1 is repeated, so that's just equal to 0. Now, I highly recommend looking at the Wikipedia page for this. It explains it better, and it even shows you a 3x3 matrix which shows these components better. But it's called the anti-symmetric tensor because if we switch two of these indices, then we're also switching the sign. But if that was true, then, and this was not equal to 0, let's say it was just equal to some number, and we switched 1 and 1, we would get minus a by the definition of this. But if a is equal to minus a, that tells us a is equal to 0. So that's why it has to be 0 for repeated indices for it to be anti-symmetric. Okay, so now we're going to apply what we learned about index notation, Einstein Summation Convention, and the Levi-Civita symbol to solve some problems. So I'm going to be doing problems from a worksheet down in the description. It's by Professor Prof here in Trinity, I think for an ACM module. So let's get started for question 1. So it asks us to check that the cross product can be defined in this way. If we take two vectors, a and b, we take their cross product, and we take the ith component of this resulting vector, that should be equal to epsilon ijk aj bk. Okay, so first of all, to check that these are equal, you probably want to know how this is defined in the first place. If you've seen this before, you've probably seen it defined like this. And there are two other components that we're not going to check in the video, but you can do that yourself as homework. Okay. So this component, this entry of this vector, is the first entry, right? So here I would be equal to 1 if we're talking about this one. So let's see if this is actually equal to that. I'm going to say A cross B sub 1, right? It should be equal to A2, B3 minus A3, B2, okay? Where here I'm saying A sub 2 is the second component of the vector A, and B sub 3 is the third component of the vector B, right? They're both three-dimensional vectors. Okay, so this is what we're trying to find, and we're going to start off with this. So if we set I equal to 1, what do we get? We get epsilon sub 1 jk aj bk. But if we refer back to our Einstein Summation Convention rule, which is that if an index is repeated, we sum over it, here both the indices j and k are repeated. So now we're going to sum over them. They can take values 1, 2, and 3. Those are all the values that they can take. However, if either j or k were equal to 1, then we would have epsilon sub 1 something 1. And we'd have a repeated index in this, which would yield 0. So we can ignore those. Similarly, if j and k are equal, but not equal to 1, so let's say j and k are both 2, or j and k are both 3, it would also be 0. So that leaves us with two options. J is equal to 2, k is equal to 3, or j is equal to 3 and k is equal to 2. So we're going to sum over those options. Now in reality, we've summed over everything, but the ones with repeated indices just vanished. Okay, so from this step to this step, I've summed over the possible values of j and k, but the only non-zero ones are when j is equal to 2 and k is equal to 3, or when j is equal to 3 and k is equal to 2. Okay, so now we just need to compute these symbols. You should all be screaming that this is equal to +1. So this is just A2, B3. And 1, 3, 2 is just one permutation away from 1, 2, 3. So this is an odd number of permutations away. So this symbol is equal to -1. That gives us A3, B2. So indeed, we found that the cross product can be defined using this, and it can even be used to find vector identities, which is what we're going to do in the next few questions. Okay, so if you've been following along with the worksheet, I'm going to skip questions 2 and 3, I believe. Yep, those are just very tedious identities to derive using the Levi-Civita symbol. Again, you'll find it on the Wikipedia page, but we're just going to take this identity as granted, okay? We're just going to assume it's true. Okay, and we're going to use it to prove this vector identity. Is equal to, and then, well, let's find it first and see if it compares well with the worksheet. I'll write out the answer at the end. Okay, so first thing to notice, we have two cross products, right? But how we defined the cross product earlier was, I'll write it down here, that the ith component of A cross B is equal to epsilon ijk, this is an epsilon, aj bk. So for one cross product, we have one Levi-Civita symbol. That means for two cross products, we'll supposedly have two Levi-Civita symbols. Good to know. Another thing to notice is this is a vector. We start off with two vectors, and we took the cross product. So B cross C is a vector, and then A cross B cross C is also a vector. So now this is a useful trick. Whenever you're trying to derive vector identities, it's always best to start off with the ith component of the left-hand side, and then work your way and see if it's equal to the right, or the ith component of the right-hand side. So we'll do that. I'll take the ith component of this. So according to this definition, that's epsilon I jk aj, and now here, it's the kth component of the B cross C vector. Okay, but what's this? That's epsilon k, and I'll be very careful here. I've been using ijk only as my indices, but really you could use any letter you want, as long as you're consistent and as long as you're aware what the range of what values that letter may attain, or that index may attain. So in this case, ijk can always be 1, 2, or 3. However, we need new indices because we've already used up j and k. Those are already taken. Those are already assigned. So we need new indices. You can call them whatever. I'm just going to call them m and n. Okay? And then it's going to be bm cn. Notice, this index is the kth component. So this is a k because we're taking the kth component of B cross C. And then it's b sub m because m is the second index, and c sub n because n is the third index, right? Which agrees with this definition here. Okay. Now, I'm going to use this identity that we took as granted. But to do so, I'm going to rewrite this a little bit. I'm going to group these. Okay. I should probably explain that this delta is the Kronecker delta. It's equal to 1 if the indices match. So for example, if j and m are equal, then this delta jm will be 1. If the indices do not match, then this will vanish. It'll be equal to 0. Okay. Now you might be asking me, why aren't these the same? Am I really able to use this identity? There's not two i's, so how does that work? Well, there are two k's. And from the definition of the Levi-Civita symbol, we can always change these indices around, and it'll be the same, as long as we change it by an even number of permutations. So let's say, for example, we brought this k over here. That would be 2 permutations, and that would be an even number of permutations away from what it started with. If you think back, if we had an odd number of permutations to start with, from 1, 2, 3, then if we did an even number from then, we would end up with an odd at the end. You know, like 2 plus 3 is 5, that's odd, because we started off with 3. Anyway, as long as we do an even number of permutations to these indices, we retrieve the same symbol. So I'm going to do that now. I'm going to rewrite this as epsilon k I j. So if you think about it, I switched k and j, and I switched k and I. And then epsilon k m n. aj bm Cn. I haven't changed these. Okay, now what do we do? Well, we're just going to plug in our identity, and we're going to be very careful with what we write for this, because I've changed the indices now. Okay. That's going to be equal to delta of the second from this one and the second from this one, so that's im, delta jn minus delta in delta jm times aj bm cn. And I'm going to bring this back to the top of the board and we'll continue. Okay. So now that we have this, and then now that we know the definition of the Kronecker delta, we can do a lot of simplification. So this delta im tells us that for this term, multiplying this, it'll only be non-zero if m and I are the same. So that means wherever we see m, we can replace it with I. What's really happening here is we're summing over m, because if you notice, m is repeated. So we're just going to sum over m until it's equal to I. And that's why we can write an bi cn. Because similarly, we're going to sum over j, because it's repeated, until the value of j attains the value of n, and we're left with a sub n. Okay. That's me minus, same thing for this one, so it's going to be a sub m, b sub m, and c sub n. And here, c sub I, because n must be equal to I for this to be non-zero. Okay. Here, we have repeated indices still, and this looks a lot like the definition of the dot product from the beginning. So all this is bi times a dot c minus ci times a dot b. But if you remember, we took the ith component of the left-hand side, so we're left with the ith component of the right-hand side, and this is equal to the ith component of b times some scalar, which is a dot c, minus c times some scalar, which is a dot b, so it's the ith component of that. So we've just proved the vector identity that a cross b cross c is equal to b times a dot c minus c times a dot b. Now, I don't know how you would have done it without this. I actually just don't even know. But using index notation and the Einstein Summation Convention and the Levi-Civita symbol, we've been able to arrive at a pretty cool vector identity. And now we're going to do another one, which is a little bit different, but uses the same idea. Okay, so now we're moving on to question 5, and I said it was a little bit different. That's because we're not starting off with a vector, so we're not going to take the ith component of the left-hand side. Instead, we have a vector dot another vector, which is just a number, a scalar. So how are we going to find this? Well, once again, we have two cross products, so we're going to have two Levi-Civita symbols. And, well, once I write it, you'll see the way forward, I think. So this is going to be, a cross b sub I, the ith component of this, times c cross d sub I. If you're confused, just look back at the definition of the dot product. We have the first vector sub I times the second vector sub I. Since the index was repeated, we're summing over that, and that is indeed the definition of this object. Okay. Now we're going to write these terms in terms of their Levi-Civita symbol. Okay, so it's going to be epsilon ijk aj bk from that. And similarly, epsilon I, I'm going to use different indices. As I discussed previously, we can't reuse j and k because they're already assigned. Okay. And now we're just going to apply that identity again. Maybe let's try and do it in our minds. So we have epsilon ijk, epsilon imn. So this is indeed what I have written on the board here, right? So the first term is going to be when j and m are the same, and when k and n are the same. I'll reiterate. We're summing over j and k because they're repeated, and m and n because they're repeated. So essentially what's happening is we're summing over these indices until they match, right? And at that point, the Kronecker delta would be equal to 1, and then we're left over with those terms. So if we sum over j and k, so it'll be delta jm for the first one. So that means j and m are going to be the same. So let's write that. I'm going to replace m with j. That's up to you. Cj. And then the second Kronecker delta tells us that k and n are going to be the same. So I'm going to replace that with k. Okay, now the second one, minus delta jn. So j and n are going to be the same. So that means a and d will have the same index. Or we're talking about the same components of a and d, is another way of saying it. So I'm just going to use, j again. And you can guess probably k and m must be the same. So bk, ck. Okay. But here we just have a dot product times another dot product minus a dot product times another dot product. Reassuringly, that's a number. This is my b. It looks like it has a little belly. This is a number. If it wasn't a number, you definitely did something wrong because we started off with a number or a scalar. Okay. Once again, a very powerful display of what index notation and the Levi-Civita symbol and its identities can do. But this is only true if only the first index is the same. And now we're going to derive another identity, which will tell us what it's equal to if the first two indices are the same. So for question 6, I'm going to show you how to calculate this, but I'm also going to give you a bonus at the end that'll sort of tie this whole thing together. Okay, so let's start. So we need to find this product given this identity. What has changed from here to here? Well, m has been sent to j. Now there are two j's, so the index is repeated, so we sum over it. What does that mean? That means we're going to write what we have there, replace m with j, right? Delta kn minus delta jn delta kj. Okay, I replaced m with j, but here, since j is repeated, we're actually summing over j equal to 1, 2, and 3. But since 1, 2, and 3 are all the values that k and n can achieve, this is going to be very important. First of all, you might see this and think, naively, that that's equal to 1. It's not. It's actually equal to 3. I'll show you why. Since we're summing over it, this is not being summed over, so we can just bring it out of the summation. That's equal to, well, we're summing over j, so that's going to be delta 1, 1 plus delta 2, 2 plus delta 3, 3. And now you can see why it's not equal to 1. It's actually equal to 3. And then we have another term that I'm going to leave for now. Kj. Okay, so that gives us 3 delta kn minus what? Well, I told you we're summing over j. But j and k can only take the same, or sorry, k can only take the same values as j. So that means at some point, k and j will be equal. At that point, for this to be non-zero, n and j must also be equal. But if k is equal to j and j is equal to n, that means k is equal to n whenever this is not 0. And if it's not 0, it's equal to 1. We have a name for that. It's called the Kronecker delta, and the indices will be k, n. So we have 3 delta kn minus delta kn. That gives us our answer of 2 delta kn. Okay, but what if we want to find epsilon ijk squared of sorts, right? Here, I replaced n with k. I'm going to sum over n. That means we have 2 delta kk. And I told you before, that's not equal to 1, that's equal to 3. So this will give us 6. And that's everything. We've done when, well, in the worksheet, you're asked to derive when none of the indices are the same between these two. We're also asked to derive when the first ones are the same, but I think you can do that yourself by now. And we just derived when two of them are the same and when the three of them are the same. So now you're ready to go with the Levi-Civita symbol. And next, we're actually going to apply what we learned to write matrices using index notation. So question 8 asks us to find J in matrix form given this definition for its entries. So I told you that M sub I referred to the components of the vector M. Well, similarly, J sub I little j referred to the entries of the matrix J. So how would you go about doing this? Well, probably, since we're only working in 3 dimensions, the easiest thing to do would be to compute these entries manually. So that means writing J11 is equal to computing it and then putting it in the matrix. So here we have J11, J12, J13, J21, J22, J23, J31, J32, J33. Okay, what are those J's? Well, J sub 11 has this definition. And already you're probably going to notice what's going to happen to the diagonal entries, J11, J22, and J33. Whenever an index is repeated in the Levi-Civita symbol, we know that it vanishes, it goes to 0. So that tells us that this is 0. But it's 0 whenever an index is repeated, which means J11, J22, and J33 will all be 0. Because I and J will be the same. Okay, that's good. That sort of leaves us with less work, and we like that. Okay, but what about the other ones? Let's start with J12. That's equal to epsilon 12 k mk. We're summing over k from 1 to 3, but the Levi-Civita symbol is only non-zero when k is not 1 or 2, so it must be 3. So that gives us epsilon 1, 2, 3 m3. That's just equal to plus 1, so that's equal to just m3. Okay, what about J13? Well, that'll give us epsilon 13k mk. Once again, k cannot be 1, it cannot be 3, it must be 2. Or rather, we're summing over k, but only when k is not equal to 1 or 3 does the term not vanish. So we're only left with epsilon 132 m2. 132 is one permutation away from 1, 2, 3. That's an odd number. That tells us that this is a minus 1, and that gives us minus m2 up here, top right corner. And now I'm going to focus on this one. I'll tell you why. If we have J23, which is that entry, that'll give us epsilon 23k mk. As before, k can only be 1, and that tells us that M1. This component is actually equal to, well, this is 1, 2, 2 permutations away from 1, 2, 3. You can see that because this is 1 permutation away from 2, 1, 3, which is 1 permutation away from 1, 2, 3. So there we go. And that'll give us plus 1. So this is plus M1. I'm going to fill in the rest, almost like magic, but I'll tell you why I know how to fill it in. So what is this entry? It's J21. Okay, why is that useful? Well, J21 is equal to epsilon 21k mk, but that's exactly 1 permutation away from this Levi-Civita symbol. If it's only 1 permutation away, that's an odd number of permutations away, and it's going to switch the sign. So let's say this was minus 1, then this will be plus 1. Or let's say this was plus 1, then this will be minus 1. So either way, J21 will be equal to minus J12. Similarly, J31 is equal to minus J13, and J23 is equal to minus J32. So all I've done is I've looked at the diagonal and I've flipped it and then I've inverted it, so switch the sign. And you'll notice this is equal to minus J transpose. Because if I did exactly that and I flipped it again, then the minus M3 would be here, minus M2 would be here, and minus M1 would be there. This is known as an anti-symmetric matrix because once you take the transpose, it's equal to minus itself. Okay, so in question 8, we found J in matrix form. In question 9, we're asked to find this lambda constant of proportionality. And we're actually going to use Jij's original definition in terms of the Levi-Civita symbol. Okay, so let's write that, epsilon ijk. And here I'm going to sub in the definition, but notice k is already in use, so I have to use a different index. So this will be epsilon ij, I don't know, we can call it L for example, ml nk. I don't have it on the board, but we're going to use the identity that says that if the first two indices of this, these multiplying Levi-Civita symbols are the same, first two indices, I think I said, then that gives us 2 times delta with the 2 remaining indices. So that's KL, and then MK, and ML, and K. Okay? Well, here, we're summing over K and L, and this will only be non-zero when they're the same index, same value. So we can effectively just write L for K or K for L and ignore the other one. That's the power of the Kronecker delta. Okay, but now we're still summing over one of them. And this is just the definition of the dot product. So that gives us 2m dot n. And if we compare the desired result with what we got, we see that 2 is equal to lambda, or well, lambda is equal to 2. That's the answer. Now, if you've come this far, I think the next question is pretty tough, but I think you can try it. It's going to be question 7. Okay, well, that's it for me. Thanks for watching. I won't be doing question 7 this video. I'll do it in the next video. So try it yourself, and then you'll be able to compare. If you found this video long and boring, that's okay. It's a hard topic to get into the first time, but I hope you found it at least somewhat instructive. And if you have any questions, just leave a comment and we'll get to it. Don't forget to subscribe to the TPSA. Follow us on Instagram. We're a growing community. And yeah, thank you.